continuing with our idea of Königsberg, using our smaller model here, let's get rigorous with the graph theory and define an Eulerian path. So an Eulerian path in a graph is a closed walk that uses every edge of G exactly once. So let me, just for ease of notation here, let's number the bridges, which are going to be the edges that we have in our graph. So we'll just go through and maybe do them systematically. 4, 5, 6, and here's bridge 7. So here are the 7 bridges, right? And again, if I were to draw this as a graph, how would I draw it? Well, I like to draw my land masses as the vertices. And then we can draw our edges. Remember, we've got 2 edges here. These are bridges 1 and 2. The bridge across here is bridge 7. This bridge is bridge 3. Here's bridge 6. And here's bridge 4 and 5. Okay, so this is how I've rendered this model of Königsberg as a graph. Okay, so what does it mean to be a walk? So a walk means that the same edge never appears twice. To be a path means I use every edge. So an Eulerian walk, so what would well, we wouldn't call it an Eulerian walk, but what's a walk? So let's do an example of a walk through this graph. So what I'm going to do is start somewhere, and as I cross a bridge, I can't cross it again. So I would say E3, which is this bridge. So starting here, X marks the start. I could take E3, followed by E7. So I have to line up. After E3, I can't take E2. Well, I could if I went that way, but I certainly can't take E5. So the edges that show up consecutively have to have a vertex in common. So I have to be able to walk across. So we have E3. Okay, now I've got E7. So now I'm here. I could take E5. And then I could take, let's take E4. And now I'm back up here. And now I'm going to take E2. And now I'm done. This is a perfectly good walk. So again, to kind of draw this out, E3. And now I can't take that bridge again. And then I took E7. And I can't take that one again. And then I took E5, followed by E4. Those are now done. And then I did E2. And then I stopped. And this is a closed walk. It's closed because I ended back where I started. Now, notice that I visited the same vertices more than once. So here, if we give these vertices names, so maybe we'll just call them A, B, C, and D. Another way that I could write this walk is I could say, okay, well, I started at A, and then I went to C, and then I went to B, and then I went to D, and then back to B, and then to A. Now, I don't want to just write down my list of vertices because that's not descriptive enough. That doesn't tell me which edges I took. It's important which edges I took. So here I would say, okay, I took bridge 3, and then I took bridge 7, and then I took bridge 5, 4, and 2. So this is one way that I could write what my walk is, and notice that I could actually draw this to finish up, to point out that I in fact have a closed walk. So that's a little better to indicate that it's closed. So having notation that we can use, that we can really get our hands on, is important as we start to try to write out theorems in graph theory. We need to be able to have good ways to talk about rigorous definitions and to do these sort of illustrative examples. So here's our first proposition, and it relates very much to the bridges of Königsberg. It says the following: if G has an Eulerian path, then every vertex has even degree. What's the degree? Well, the degree is the number of edges that comes out. So over here, I can make a list of my degrees. The degree of A is 1, 2, 3. There are 3 edges adjacent to A. The degree of B, this one is 1, 2, 3, 4, 5. And the degree of C and D are also 3. So this is also the degree of C and also the degree of D. So from this proposition, once we prove this proposition, this shows, therefore, we have a corollary. We cannot traverse Königsberg. Königsberg's, let's say, 7 bridges in an Eulerian path. Why not? Because if we could, then the degree of every landmass would be even. In fact, the degree of every single one of them is odd. So we really can't do it. There's no way to solve it. And this proposition is what tells us that we don't have to check all the cases, right? As graphs get bigger, it becomes much harder to check the cases. So we want to have powerful theorems like this that tell us we can just look at a simple property that we can check, even on a large graph, to conclude something very powerful about the existence, or in this case, the non-existence of a Eulerian walk, Eulerian path. So let's do a proof. I'm going to start out this proof, and we're going to think about this idea of walking the mountain and writing out what happens to the path. So before we embark totally on the proof, think about this. Whenever I write down a walk, okay, how many edges have I used for each vertex? So for any walk, I guess we will start the proof. Okay, if we take a walk, and we're going to let our walk be E1 up to En, okay? A path is an example of a walk, and it uses every edge exactly once. But a walk doesn't repeat edges, right? But in any walk that I have, notice how many edges I get, right? How many edges are used for A? How many times does A appear here? It appears once, which means that it's got 2 edges. So we get 2 edges touching A in this walk, okay? What about for B? B appears twice. That's okay, it doesn't matter. Each time B appears, it gets 2 edges. So it's going to have 4 edges. And what about C and D? Well, C appears once and has 2 edges. What about D? D appears once and has 2 edges. So this walk, which has 1, 2, 3, 4, 5 edges, has these multiplicities in terms of how the edges appear. And that's the crux of the proof. That's actually how we're going to prove this theorem. Just by looking at this example and thinking about, oh, when I have a walk, what's the degree within the walk? If I just took the edges of the walk, what's my degree? When it's a closed walk, it's always going to be even for every vertex. When it's a path, we've already used up all the edges, and that's what tells us we can't get a path. So let's write that down rigorously. Maybe I'll respect the fact that English goes right to left. Sorry, left to right. One of those directions. Okay, so let's write down our proof. So we're going to suppose that we have an Eulerian walk. So suppose, let's call it E1 up to En is an Eulerian walk. And let's suppose further that we have, let's say V0 goes by E1 to V1, and then we go to V2 by E2, and we keep going, and we're going to go up to Vn minus 1, so this will be En minus 1, and the last one is going to take us back, just the same as the situation we had before, only now I'm rendering it in notation, right, instead of in a concrete example. So suppose we have this, okay? And what we're going to do is think about any vertex. So let V be any vertex. Then what is the degree of V? It equals 2 times the number of times V appears in V0 all the way up to Vn minus 1. Okay, why is that? Well, each time it appears, you get 2 edges. And of course, I'm going to assume no loops. So maybe I should make that. We can easily do something with loops. Loops add, so we're going to say no loops. Loops are special in that we consider a loop, if it comes from a vertex, as having degree 2. So it's not going to change the validity of the theorem, but for the proof, let's just assume no loops. So when we do that, the degree of V is going to be twice the number of times it shows up in this list. Okay, and that's actually the end of the proof. That implies that all V have even degree. It's that simple. Once we realize this, once we make this powerful observation, now we see that, okay, everything has to have even degree because every edge in the graph shows up here exactly once. So this is the total degree of the vertex. It's not just on this walk because this walk is actually an Eulerian path. It hits everything exactly once.